this video, I'm going to go through what are called the properties and laws of logarithms. We'll start out with what are referred to as the three general properties of logarithms. I have them listed over here, and we'll just kind of quickly discuss each one of them. And once you kind of get your brain wrapped around a logarithm and what it is, they're almost self-explanatory. So remember, just to refresh your memory, if I said to you the log of x to base b equals question mark. What you're trying to figure out with this is you're trying to figure out b raised to what exponent will give me x. Right, so remember, logarithms are exponents. You're trying to figure out an exponent that you would raise this base up to in order to get this value, which is called your argument. So if I go to this first property, this is saying the log of 1 to any base is always going to be 0. I want you to think about that. This is saying a, some base, raised to what exponent will always have to give me a 1. Well, we have a property in mathematics with exponents that any base to the exponent 0 is always equal to 1. So therefore, it doesn't matter what this base is. The log of 1 to any base has to be 0. So that's a property that you should be familiar with. The log of 1 to any base has to be 0. Our second property here says that if we have the log of a to the exponent x to base a, the answer's got to be x. And again, self-explanatory if you understand what I showed you up here. This is saying, ignore the right side for a second, this is saying a raised to what exponent will give me a to the x. Well, one would say that's obvious. It's got to be whatever this is, right? The log, a to the 5 would equal a to the 5. So the question mark's got to equal the x. So therefore, if you're saying a to what exponent gives me a to the x, the answer's got to be the exponent x. A numeric example of that would be, let's say I wrote down here the log of x cubed to base 3. Sorry, to base x, not base 3. The log of x cubed to base x. So this is saying x raised to what exponent will give me x to the 3? Well, the answer's got to be 3. So essentially what I'll tell students is if the base here is the same as the base of this argument, then the answer's got to equal that exponent, just based on what a logarithm is. This last property, it's not, you don't, the first two you see lots. The last one, you don't see it written this way very often. There's not very often your exponent is a logarithm, but I want you to think about this. Imagine that I just change this whole thing. So this says that you have a base and you raise it to an exponent that is the same base as this exponential statement you're trying to make here, then the answer will be the argument of this logarithm. So to show you why this has to be true, just imagine that I took this and put a question or put a happy face here instead of that. So the rule would be, if I switch it to a logarithm, the log of x to base a would have to equal the exponent, which is, in this case, my happy face. So underneath my happy face is the log of x to base a, which this is. So just switching notations from exponential to logarithmic verifies that this exponent here, the argument turns out being this value over here. Again, that one, as I said, it's not quite as popular. So I'm not quite as concerned with that one. But the first two, make sure you got your brain wrapped around for sure, because you will see them. And this one you will see from time to time, just not nearly as often as these two. So that third one, just to show you, so I don't get it. What does that mean? That means this: if I had 4 to the log of 7 to base 4, so this base is 4. The exponent is a logarithm that's also base 4. The answer's got to be the argument. That's what this is saying. So the answer would have to be 7 without me doing anything. Oh, sorry. Okay. So now we're going to look at what are referred to as the laws of logarithms. So they very much parallel the laws of exponents. So just before I kind of get into them, so just keep in mind that when you do your laws of exponents, when you're multiplying, you add exponents. When you're dividing, you subtract exponents. If you have an exponent raised to another exponent, you multiply those exponents. That will become very much a key parallel between the laws of logarithms and the laws of exponents. Okay, so there are three of them. There's the product law, which we'll do first. These are just kind of your criteria. So A, being your base, always has to be, can't be negative, and it can't be 1. We're also going to talk here about the arguments are going to be positive, which if you think about it, that has to be true, because if this base is a positive number, there's no way you can take positive numbers raised into some exponent and the answer ever turn out to be a negative. So your argument is going to have to be greater than 0 as well. They go through the proofs. So kind of maybe we'll walk through one of them. I'm not going to go through these in any great detail. At the very bottom is the actual the product law. So it's just saying if you set up two logarithms, log of m to base a to base equals b, you take the log of n to base a, we're going to say make it equal to c. Then you switch notations. So from a logarithm to an exponential, a to that exponent would have to equal m. A to that exponent would have to equal n. And then they're going to write this as a product, the log of mn to base a. Then they go up here and they say, well, instead of m is equal to a to the b. So they replace m with a to the exponent b. Instead of n, it says here that n is equal to a to the exponent c. So they replace the variable n with what it's equal to, a to the c. And the reason they're doing this is they're going to establish that property that I explained to you on the last slide. Laws of exponents here would say I can add these exponents, and because the bases are the same. So therefore, instead of having this, we can write it as a to the b plus c. Well, notice now that this base is the same as this base. So one of the properties of logarithms was that if you have the log of any base and the argument here, so if you have the log of b to the x to the same base as this, it has to equal x. So that's exactly what this situation is. You have the log of a to some exponent to base a, the answer has to be the exponent. Then they just do a resubstitution and say, well, what's b equal to? Well, it says up here, look, b is equal to the log of m to base a. So they replace b with what it's equal to. What is c equal to? Well, c is equal to log of n to base a. There's what c is equal to. So it shows us what we call the product law. The product law says that if you have the log of a product, you can write it as the sum of two separate logarithms to that same base. So there's a couple quick examples of it down here. So I always tell students, I don't know if you're familiar with an accordion. An accordion is a musical instrument that looks like a, I don't know how to describe what it looks like. You play it out in front of your chest and they stretch it out and then they squeeze it back together. I think sometimes they call them a squeeze box. So you stretch it out, squeeze it back together. Well, these laws of logarithms, it's important you're able to go from a single out to multiple, but you also have to have multiple logs and be able to work backwards and write it as a product. Just depends on the question. So you have to be able to work these in both directions. Single, stretched out to multiple, or multiple, squeezed back together to a single. And I have an example of each. Now, these are real basic ones. We'll do more complicated ones a little bit later on, but this is just to show you what this means up here. So right here, I've got the log of a product, which means I can change it according to this law. I could write it as the log of 6. Notice the base is 10. Remember in the last video, we don't actually have to write it in there. If you don't put any base, it's assumed you mean 10. So I'm just going to leave it out. And then this would be plus the log of 9, because so I had a single log, base 10 of a product. According to this, you can write it as two separate logs added together to the same base, whatever base this is. Okay, this would be the opposite. I've got two logs. They're both base 2. Now that's key here. They have to, it's like laws of exponents. If this is log 2 and this is log base 3, then you can't use this law. They have to be the same base. So they are the same base. They're two separate logs added, and you can write it as log of 12 times 7 to base 2. You could even go further if you want and say, well, that's 12 times 7 is 84. So the log of 84 to base 2 and this the log of 12 to base 2 plus the log of 7 to base 2, if you were to figure out each of those, Add them together, get an answer. Do the log of 84 to base 2, get an answer. They are equivalent based on what's called the product law. The next law is called the quotient law. So quotient law is used when you've got the log to some base of a quotient. So two things divided here. So the argument is a quotient. It goes through kind of the whole same process. I'm not going to go through that in any great detail. You could kind of stop and look at that if you ever needed to. This is what we really need to know. The log of a quotient is equal to, and I think you could have predicted this, think of laws of exponents. Sorry about that. Think of laws of exponents where you subtract when you're doing division. It's the same with laws of logarithms. You can change a quotient into the difference of two separate logarithms. And again, as we said in the last one, you have to be able to go in both directions. So if I have a difference, I'll be able to write it as a quotient. So let's look at a couple examples of each of those. So the first one, if you have the log of 97 over 62 to base 2, well, according to the law up above, scroll up a tiny bit so we can see it. If you have the log of a quotient, like I have here, I can change it into two separate logs subtracted. It stays the same for both of them. I have two separate logs, the same base, both base 2, subtracted. So this one, I'm going to express it as a single log. Equals log of 15 over 3 to base 2. 15 over 3 is 5. So you could write this as the log of 5 to base 2. Here's a log base 10. So let's realize we don't really need to write that base in there. It's a quotient. So I could write it as the log of 1. Take away the log of 9, which equals, see if I can throw you for a loop, the negative log of 9. So we say, what? What happened to the log of 1? Where'd that go? Remember a slide ago, the properties of logs? We said that the log of 1 to any base is equal to 0. So I know that this is actually just equal to 0. So 0, take away the log of 9, would have been negative log of 9. What happens is sometimes if you're just in a textbook or something, you're looking at it, they write this down, then they write this down, and then students are puzzled and say, what the heck just happened? Where did this go? So at least in a video format like this, you kind of get a bit of an explanation of what happened to this, why it disappeared. Okay, so that's the quotient law of logarithms. There's one more. It's called the power law. Just like it, again, parallels exponent laws almost to a T. Here's your formal proof of it, which you can, again, it models the same format we used for the first example. So basically, the way this one works, without me going through it in any details, is that if you have the log of an argument raised to an exponent, now you have to be very careful here. It's just the argument, it's just the argument raised to the exponent. Where students get caught on this one is, let's say I had the log of A, base A, log of M, and the whole thing was in brackets to the P. That's not the same as this. In this one, the only thing raised to the exponent P is the argument. In this one, the whole logarithm is raised to the P. This is not power law. It doesn't work in this scenario. Okay, so it's important you see the difference. Versus this one where it's just the argument raised to an exponent. Another way that this can be written, so if I wanted, for example, the log of M to base A, if someone puts an exponent right here, not over the M, over the logarithm, that's another way of indicating that you mean this. It means the log of M to base A, the whole thing squared, which would not be power law. So it's really, really critical that you analyze where the exponent is and what's being raised to the exponent. It must be just the argument. If it's the argument raised to an exponent, what you are able to do is bring that argument, or sorry, that exponent out to the front and write it as a product. And the reason it parallels exponent laws is because if you have x cubed and you raise it to the fourth power, you multiply the exponents. In this one, if you have a logarithm of an argument raised to an exponent, you're able to bring the exponent to the front and multiply. That's the parallel. But again, it's not exact, I get that, but it parallels what happens with laws of logarithms. So then it would be that exponent multiplied by the logarithm with that exponent removed. So if we just look down here at this, what we've got, this one, so I've got the log of 8 to the exponent 9 to base 10. Remember, base 10, I don't have to write the base there, it's understood. I'm just going to bring my exponent to the front. Oops, that a little bit here, 9 log 8. That would be another way to write this expression. Opposite, let's take the 2 that's a coefficient, let's put it back as an exponent. And sometimes we will do that. Log of 5 to base 3. So it's actually the log of 5 squared to base 3. So now sometimes students will look at this one and say, well, there's no exponent here. Yeah, there is. Remember, square root is the same thing as the exponent 1/2. So that 1/2 could come to the front. And if you're starting to get the hang of this, you might look here and say, hey, wait, I can figure this out. Because this is trying to get me to say, what's 5? What exponent would I raise base 5 up to in order to get 125? Well, it's 3. So this whole thing right here is really just a 3. And that whole expression could be changed to 3 over 2. Okay, so that's using the power law. I just want to show you, before I get to trying to do a random example here that I'm going to make up. If I kind of have all of the laws together, so let's say I have the log of, I'll use base x. I'll go a cubed b squared, divide that by c to the fourth, and d, well, let's say I don't put an exponent in that one. And I wanted to separate this into a bunch of separate logarithms. Well, so this is going from single, right? This is a single log. I want to stretch it out to multiple logs using my laws of logarithms. So I'm going to work down here to show you. Well, what I just showed you is that if you had, so you can take this, and it kind of looks overwhelming when you start putting all of this together, but it's really not. It's quite easy to manage. All you got to realize is this. These ones here in the numerator are multiplied. These ones down here, they're going to be divided by. So technically, it's going to be the log base x of a cubed plus log base x of b squared. I'm not putting the exponents in. Yeah, I guess I'd rather that bracket was there, but it really doesn't make any difference. Now, then it would be minus the log. These two are multiplied together, right? So technically it's minus because of the division, but then you have a product down here of c to the fourth plus log base, what's my base here? X, right? I forget my base x, base x. Well, then this negative would distribute to both of these. So to condense all that, what I always tell students is it's real simple. If the factors are part of the denominator of a quotient, they're going to end up with a subtraction in front of them. Exponents are going to end up out in front of the logarithms. So this is kind of showing you an intermediate step, but once you get the drift of this, I would love for students to know, just do this. They're going to go, so they know these two are going to be added because they're multiplied in the numerator. These two are going to end up with subtraction in front of them because they are a product, but the negative is going to distribute into both of them. If there's 3 of them there, they're all going to get negatives eventually, and they're all going to have subtraction in front of them because they came from the denominator. These exponents are going to end up in the front. So it's going to look like this. 3 log of a to base x plus 2 log of b to base x minus 4 log of c to base x minus log of d to base x. So that's going from a single logarithm with quotients and products and exponents all in it, stretched out to a bunch of multiple logs. Notice the ones that have subtract in front of them. Those are the ones from the denominator. Those with the addition in front of them are the positive ones. They are the ones from the numerator. And notice all of your exponents, they end up as coefficients in front of the logarithms. Again, we'll practice more of this in a bit. Let's look at one doing the opposite. So I want to go from multiple to singles. Multiple logs, and we want to turn it into a single log. Well, if I could get it to look something like this, log of, let's use a number this time for the base. So log of x, let's put a 3 in front of it. 3 log of x to base 2 minus 2 log of y to base 2 plus 7 log of, I don't want to use, let's use a different letter. Let's go with w to base 2. Let's put another subtract. For fun, let's put a 1/3 log of z to base 2. Okay, now I'm just going to write the answer without doing any work of this as a single. I'm just going to get you to look at it, and I'll explain it. But I just want you to look at it and say, oh, I see what he did. That makes sense. This is what it would be as a single log. And I'd love for you to get to this point where you just go log base 2. I see a bunch of logs, all base 2. Added and subtracted. Now they have coefficients. So remember coefficients. Here I am looking to do what I said I wouldn't do. Exponents ended up as coefficients. So that's the last thing I'll say. Here's the answer. Log base 2 of x cubed w to the 7th over I squared cube root of z. There's my answer. Did that all at once. Here's how I did it. So again, pause if you're trying to think, what did you do? Here's what I did. I knew that this 3 must have been an exponent because it's a coefficient. So that could have went there. This could have went up here. This could go back up here. This 1/3 could go here. And then I know, hey, fraction exponents, 1/3 is the same thing as cube root. Oops, 3. So I just wrote it as cube. And I could have easily put z to the 1/3 here. It would have also been correct. But I just wanted you to make that. Every time I can make you think about fraction exponents are actually radicals, the more likely you're going to be to readily notice those when you see them somewhere else in the future. Notice that there was subtract in front of this one, and there was subtract in front of this one. So on my last little example, I said, if they're part of the denominator, they will end up with a subtraction in front of them. So if I see a subtraction in front of these ones, that's why they ended up down here. These ones were positive here and here. That's why they ended up the factors in the numerator. So that would be how you go from multiple logs and you squeeze it back to a single log using your laws of logarithms. So let's just look at some quick examples here. So now these ones start out pretty easy. So here's the first one. I've got, I might be able to put my equals beside them. This is a quotient. So it would be log base 6 of x subtract log of y to base 6. Now this one, if you look at it, the whole argument is raised to the 1/2. So I'm going to go 1/2 log base 5 of xy, and then say, why don't you separate that? Because it wanted individual log x, log y. Doesn't want multiple variables in your log. So this one's going to then be 1/2. You could just put a bracket here if you want and go log of x to base 5 plus log of y to base 5. Sometimes a student B might have put the 1/2 in front of each one of these. Obviously, that's the same thing. All right, let's see if we can do this one all at once here. So this one would be the log of 9 to base 3, subtract the log of x. Now my exponent will be, so it's cube root and you're squared, so that's the exponent 2/3. And the base would also be 3. I'm just going to keep going sideways here because I don't want to get in front of this one. I could actually figure this out and put a number for it. The log of 9 to base 3. This is saying 3 raised to what power gives you 9? That's a 2. This is, it wants just log x. It doesn't want x to the 2/3. Let's bring the 2/3 out front. And I'd have log of x to base 3. Last one. Let's see if I can do it all at once here. So I'm going to go 5 log x to base 7 plus log of y to base 7 subtract 1/2 the log of z to base 7. So the reason the half is here is because this is really z to the half, and remember exponents can end up as coefficients. That's why the 5 ended up out in front of this one. Notice the 2 that are plus came from the numerator. The one with subtraction in it came from the denominator. All right, let's do some examples of the opposite. Multiple logs. Oh, this is still a single log, I guess. This one just says use laws of logarithms. So they want us to get an actual number for these. They don't want us to just type it in your, some of you can cheat. You might have the calculator feature that lets you just type these exactly in. You can put any bases in. Again, that's not very common on calculators. There are a few that will do it, but most of you will only be able to do base 10. So you need to, everyone needs to learn how to navigate these without a calculator, because especially if you end up at a university, a lot of your introductory math courses, you don't have a calculator. So let's look at this one. What I notice here is that the base is 3, and these numbers are powers of 3. So how about we just split it up a little bit? Let's do it down here. Log of 9 to base 3, because 9 radical 3 means they're multiplied together. So this is a product. So I can write it as a sum. Log of radical 3 to base 3. So this is saying 3 to what power gives me 9? That's 2. This is saying 3 to what power gives me square root of 3. Now some students might struggle a little bit with that one. So let's change radical 3 to 3 to the half. Well, this is one of the properties I mentioned at the beginning of this video. This is saying 3 raised to what exponent gives me 3 to the 1/2. Well, this whole thing should be able to be written as a half. Well, 2, which over 1, which is 4 over 2, plus 1 over 2, that's just equal to 5 over 2. So I evaluated that. You could have done that without using laws of log. You could have done this right from the get-go. Just put an or here. Just said log, and could have recognized that, hey, these are powers of 3, and this is a power of 3. I'm just going to get this turned into 3 to some exponent. So you go 3, change 9 to 3 squared, change 3 to 3 to the half, or sorry, square root 3. Use laws of exponents and add your exponents here. And that would give you 3 to the 5/2. And then it's that first or second property of logarithms. This is saying 3 raised to what exponent gives you 3 to the 5/2. Well, it's got to be 5/2. So it's a different way to do it, both 100% fine. Part B, the log of 1,000 to base 5. I'm going to take these and just put them on a new page. Just going to pause for a second. All right, there, I got everything copied. Here we go. So let's have a look at this one. So I'm trying to get the value of this. I'm not using a calculator. I'm just going to try and use laws of logarithms to help me out. So what I notice here is 2 of them have subtracted. Well, before that, I notice they're all base 5, and it's logs added and subtracted. No coefficients, so I'm not going to deal with that. I'm just going to write this as a single log. Oops. Single log of 1,000 over, because these are both subtract, they're both going to go to the denominator. That's 6, that's 0. And the base here is 5. So this is 1,000 divided by 8. And 1,000 divided by 8 is 125. So now I'm trying to figure out, well, 5 raised to what power gives me 125? 3. So hopefully we're starting to get more comfortable with this, and you will, hopefully, as you're doing some practice, you kind of start to recognize how you quickly evaluate these logarithms. There's that one. I got one more here. So this one's similar, except it's also got the exponents out in front. So we'll deal with those at the same time. So let's do the same thing. Log base 3. It's a bunch of logs. They're all base 3, addition, subtraction. Again, this time make sure you deal with the coefficients. This one is the only subtraction one, so that'll be part of the denominator. These two will go to the numerator, so it's going to be 6 squared multiplied by 2, right, because those are added. And then this one is going to be 64 to the exponent 1/2. Exponent 1/2 means square root. All right, let's clean this up and see what we got here. So we got log base 3 of 36 times 2, that's 72. Square root of 64, that's 8. 72 divided by 8 is 9. And a log of 9 to base 3 is saying 3 raised to what exponent gives me 9? The answer's got to be 2. All right. So that is your laws of logarithms being put to work, showing you how they work. Let's look at these ones that have variable expressions in them. So I've got 4 log x. What I often recommend students do here is, let's take a, for example. I would maybe go 4, log x base 3. Distribute that half into these. So I got minus a half log of x base 3. This negative is going to go in here, make it negative 5 over 2 log x base 3. So I always encourage them to distribute any coefficients in through brackets and just have it so it's a bunch of separate logarithms added and subtracted. And then we should be in the position to go to a single log in simplest form. So let's go log of, well, I'll show you 2 ways. So I can take this one and I can write it as the log of x to the 4th over, because these are both subtract, they're going to be in the denominator, so it's going to be x to the half times x to the 5/2, both part of the denominator because of the subtraction. Ugh, it's a bad 5. Let's see if we can make it out. Okay, that's my 5 over 2. Then I'm going to use laws of exponents to continue further with this one. Good. Oh, I forgot my base. My base is 3. So this will be the log base 3 of x to the 4th. Laws of exponents is I can add those. So that's going to give me 6 over 2, which is 3. These are both base x's, so I can use my laws of exponents and say that this is the log of x to base 3. That would be the simplified version of that expressed as a single logarithm. What you could have done, logarithms are like variables. Like, see how I've got log of x to base 3, log of x to base 3, log of x to base 3. I can just collect those together. I'll show you with an easy example first, an easier one. So let's say I had 5 log w to base b plus 4 log w to base b. Well, because these are exact same, they're considered like terms, I can collect those together and say I've got 9 log w to base b's, because there's the same logarithm. Well, I can do that here. This, and this are all the same logarithm. I could have collected those right from the get-go and said, well, it's 4. Maybe let's put this, that's 4 over 1. Let's put, because I see these are over 2, let's say this is 8 over 2. Take away 1 over 2, so that's 7 over 2. Take away 5 over 2, well, that's 2 over 2, which is just 1. 1 log x to base 3. Notice what I got. 1 log x to base 3. Same thing. Let's look at b. b is, it's a quotient. Now here is, I'm going to show you something that is by far the most common misconception by a student. Okay, so I'm going to put this first, and I'm going to reinforce you. This is incorrect. Incorrect. Students will think that this out front here is like having a constant, and they'll distribute it into a bracket. They'll say, oh, this is easy. It's the log of x squared to base 2 minus the log of 9 to base 2, which is absolutely incorrect. This is a mathematical function. It does not have distributive properties like a number or a variable does. I always compare it to trig ratios. Let's say I had the sine of x plus y. And again, some of you may think this is true, but it is not. The sine of x plus y is not the sine of x plus the sine of y. That is incorrect. That doesn't work that way. You can't distribute a mathematical function into brackets like you do a constant. So having said that, so what do I do? Well, you don't do anything with it other than maybe some factoring later on. We'll get to that. So let's erase this stuff out. So everyone sees what you're not allowed to do. Do not distribute a function, logarithm, or trig function through a bracket like you do a number or variable. They don't. They don't have distributive properties. Get rid of this. So what I should do here instead is notice that I've got log base 2 with a subtraction in between them. I can write that as a single log. Base 2 of x squared minus 9. The subtraction goes to the denominator. And then just try and simplify this expression if you can. Well, hopefully you folks are competent enough in your factoring to see there's obvious factoring here. Let's factor this to be x take away 3, x plus 3. Let's factor the denominator to be x take away 3, x plus 2. These divide each other out, and here's the simplified version. Log base 2 of x plus 3 over x plus 2. That's written as a single logarithm. So this just summarizes your laws of logarithms. So I'm going to show you a common type of question that we'll run into. Let's see if I got one here. Just give me a second. Okay, so I got my last two examples ready here for you now. So this, at first glance, you say, wow, look at this. So I have a bunch of logarithms. And I want to write it as a single logarithm in simplest form. Now I have to watch for brackets. Here's what I recommend you do. And there's, again, I'm giving you a plan that I like, that works. There's probably 50 different ways to do this question and get the right answer. My personal preference is to, number one, get rid of any any brackets. So I'm going to start in here. I'm just going to distribute this 12 into this bracket. That's the only spot, so I'm not going to do too much at once here. So it's going to equal 3/4 onto 12 log of x squared to base b minus 24 log of x to base b. So I've just distributed the 12 into each of these two terms. Still have my plus 8 log base b. I'm going to write this as x to the half. And then minus 4 log base b. And instead of 1 over x to the 7th, I'm going to write that as x to the negative 7th. Now I'm going to bring 3/4 into each of these coefficients. Now 3/4 of 12, so 4 goes into 12 3 times 3 is going to give me 9 log of x squared to base b. 3/4 of 12, 4 goes into 12 6 times, multiplied by 3 minus 18 log of x to base b. 3/4 times 8, so 4 goes into 8 twice, times 3 is 6 log of x to the 1/2, and 3/4 of 4, so 4 goes into 4 once, times 3 is going to give me 3 log of x to the minus 7 to base b. Okay, so no more brackets are left. I've got a bunch of things now added and subtracted. If you're really good at it, you can go right to the final answer. If you're just kind of in the beginning stages, where most of you are, I recommend maybe one more line. And what I call it is return all coefficients. So if there's a number in front, like this 9, take it back up here. Now, if there's already an exponent there, you're going to have to multiply these together. So this first one's going to look like this. Log of x to the 18th to base b. Now, I'm going to leave the subtract sign, and just the 18 is going to go. So minus log of x, there's a 1 there, so 1 times 18 will be 18 to base b, plus, take the 6 up, log x cubed, got my base here, base b, to base b. Take the 3 up, so I'm going to leave subtract, log base b of x to the negative 21. Okay, so now I'm going to go single log base b. Anything that's positive is going to become part of the numerator, so this one and this one are going to go to the numerator, so x to the 18th will get multiplied by x to the 3, and then I'm going to have x to the 18th times x to the negative 21, because that one's got to subtract in front of it, so it would be a factor from the denominator. Now we're going to tidy this up and we want it in simplest form. So the nice thing is they're all powers of x, so we're just going to use laws of exponents now, log of base b. So the numerator, when you multiply those together, you're going to get x to the 21. You add the exponents. Here you're going to get x to the negative 3. Now they're both the same base. You can subtract these exponents. 21 subtract a negative 3 is the same as 21 plus 3. So that's going to be x to the exponent 24, which sometimes students will write like this, 24 log of x to base b. They just bring their exponent to the front. They're both right. Single logs in simplest form. Okay, so that gives you a bit of a strategy to work through a really, so that's a really complicated laws of logarithms one. Kind of we're at the extreme end of how challenging they would get. And I was able to get it down to a single logarithm in simplest form. So the next one is sort of the opposite. These are real common questions, so I want you to pay attention to what happens here. They tell you what the log of x to base r is. It's some number. The log of y to base r is that number. And the log of z to base r is that number. I apologize, the quality of the image isn't great here, but we'll get through it. So this is log base r. That's good. It matches up with these bases. This is cube root of x to the squared, z to the 5th, r to the negative 3 is in the denominator, y to the 4. So notice the cube root is only over the 2 in the numerator. So what I'd want to do, because I want to get log of z to base r, so I can replace it with the number 9. So I got to kind of whittle away at this and get it expanded out to a bunch of multiple logs. So I'm going to take the top one and say it's log base r of x. Now, cube root means take a third of the exponent that's already there. So it's really going to be x to the 2/3. They're multiplied. So it's going to be log base r of y, or not y, z, sorry, plus log base r of z to the, oh, what happened here? It should be 2/3. This one would be 5/3. Cube root of z to the 5th. These are in the bottom, so it's going to be subtract log base r of r to the negative 3, subtract, because it's a factor from the denominator, log base r of y to the exponent 4. Now where students go wrong is they say, oh, I'm just going to fill this in, log y base r, with negative 2. But this whole thing is not raised to the 4th power. If it was, you could do that. But it's just the y raised to the 4th power. So I can't make that substitution. I need to do one more step. Bring your exponents out as coefficients using the power law of logarithms. 2/3 log of x to base r plus 5/3 log of z to base r minus a minus 3, so that's really going to become plus 3 log of r to base r, take away 4 log of y to base r, so y. Now you can make your substitution. The log of x to base r, I'm going to replace it with what it's equal to, negative 6. So I'll just underline those. See this here? Log of x to base r. It says right here, log of x to base r, you can replace with that number. So I'm going to put negative 6 in there instead of that. The log of z to base r, I'm going to replace that with the number 9. the log of r to base r, I'm going to use my property of logs. You say, oh, they didn't give me that one up there. I don't need it because these are both the same. It's got to equal your exponent. So that's going to look, that's just going to be one of your properties of logs. That's just going to be equal to the number 1. And this one, the log of y to base r, we are going to replace that with a negative 2. So these 3 we have substitutions for up here. This one we're going to use our knowledge of properties of logs to figure that one out. So here we go. It's going to be 2/3. Log of x to base r, we're going to replace with the number negative 6 plus 5/3. Log of z to base r is the number 9 plus 3. Log of r to base r, this is saying r raised to what power gives you r? Well, it's going to be 1 minus 4. The log of y to base r was given, it's a negative 2. So now I've got a numeric expression here that I'm going to calculate. Remember, this is over 1, over 1, over 1. This will be negative 12 over 3, negative 4. This will be 5 times 9, which is 45 divided by 3. That'll be plus 15. 3 times 1 is 3. Negative 4 multiplied by a negative 2 will be a plus 8. So that gives me 15, and 3 is 18, and 8 is 26, and a negative 4. This expression is equal to positive 22, which is the correct answer. I checked it before we started, so I know I made a mistake. That is your correct answer. So that's a real common way they get you to take a single log and separate it out as multiple logs. And again, that's a pretty common. There's some in your textbook, the practice ones are much easier than this. So if you can kind of get your brain to follow what I did here, you'll be fine with the ones in the textbook. All right, so we're at the point now where you're going to do some practice in your textbook, some good examples. These set of questions on page 400 and 401 involve properties and laws of logarithms. One quick video left to do on logarithmic and exponential equations that will wrap up this component of the unit on exponential functions. So best of luck with these questions. And again, always reach out if you're having trouble. We'll have one more assignment to follow later next week.